So even though I've added water into the air, it's much lighter. Just kind of the opposite of the way it feels on that hot, muggy August day. You'd swear it was twice the weight, wouldn't you? But it's actually quite a bit lighter. So, what's driving all of this? If I'm looking at circulation, why is there wind? What's happening out here? And it's the simple fact that Earth doesn't heat very evenly. If I look at a square meter of solar light beam, right here at the equator, it's dead on. I mean, it's a meter of Earth that's getting warmed up, a square meter. But if I take that same square meter and it comes in closer to the poles, because of the curvature of the sphere, look at the area that it's going to be spread over. Way more than a square meter. So here, it's pretty effective. It's a one-to-one match. That square meter is getting nicely warmed up. Up here, this square meter of sunbeam has about 3 square meters of land to warm up. Much less effective. So the poles are cold, the equator is hot. If we didn't do anything about it, if there was no mechanism to redistribute this heat more evenly around Earth, the water at the equator would literally be boiling. It would be so hot it would be boiling into vapor and leaving the surface of the ocean. The poles would be frozen solid right down to about here in Kalamazoo. That doesn't leave a whole lot of space for life to really flourish on Earth, does it? So we have some pretty severe extremes with not much ability to have life in between. So we've got to somehow spread this around. Well, if this is where it's heating the most at the equator, that's where the air is going to be rising, isn't it? Hot air rises. So I'm going to see this air rise, and as it does so, it's going to be cooling, and eventually it's going to hit a point where it's not going to rise anymore. You know, it's cooled off. This rising of hot air effect is pretty much done, and it's just going to kind of start spilling off sideways. It's got more hot air coming up from down below, and it's kind of pushing it off to the sides at the top. So I'm going to start to see hot air rising, and some of it's going to spill toward the North Pole and some toward the South Pole. So that's great. I'm going to be pushing air, warm air, up toward the poles. At the same time, this cooler air up here by the poles, it's going to be sinking. It's cold air. It's going to be sinking, and it's going to be creeping along the Earth, picking up some warmth from the Earth, moving toward the poles. So I'm taking this cold air, and I'm moving it down here with its energy. I'm taking the hot air, moving it up there with its energy. So life should be pretty good. I'm equalizing the hot, cold around Earth. And you'll notice that I've done this essentially by convection. The same process we talked about in the mantle that was driving plate tectonics, this hot material moving upward, spreading out under the crust, cooling off, sinking back down at the subduction zones to be reheated and recycled again. Same type of thing, only we're using air. Kind of think of it as the radiator and the hot air rising, cooling, going along the ceiling, cooling off at the window, sinking, moving along the floor. Very effective way of moving heat and energy because I'm moving all the material and it's just taking all the energy with it. It's not like conduction where I'm just touching a hot metal bar to a cold metal bar and that one little spot of contact is transferring energy. Here, everything's moving. So this is a very effective way of doing it. So I've got this model of heat rising at the equator, moving heat to the poles, cold at the poles sinking, creeping along Earth, getting back to the equator. That would kind of mean I've got like a bowl around the northern hemisphere and a bowl around the southern hemisphere, making up these circulation patterns. But it isn't quite that simple. Because what we see happening is this air rises at the equator and starts spreading out north and south. It starts cooling off pretty quickly. And it just doesn't get anywhere near the pole before it's cold enough that it starts to sink back to Earth. In fact, it only gets up to about the 30th parallel, 30th latitude, north and south. So what I'm going to do now is just talk about the North Hemisphere. It's the same in the South Hemisphere, but let's just kind of keep it simple. We'll just talk about it. So here I am at the equator. Nice, toasty, equator hot air rising, and that means it's nice and warm air. It's got a lot of moisture in it, doesn't it? It can carry a lot of moisture. But as it rises and starts to spread out and cools off, it quickly hits that adiabatic dew point, and it can't hold all that moisture. And all that moisture now starts coming out of the system. So as I move away from the equator, what have I got? I've got the subtropics, right? And the subtropics are noted for rain and rainforests. Okay, they're still hot and steamy, but I'm dropping the water out of the system. The system's cooling, and by the time I get up to the 30th parallel, that air is cold, it's dry, and it's sinking back to Earth. Okay. As it finally gets back down to Earth, it's warm again. It's been compressing on its way down. It's getting near to the warm Earth, so it's warmed up, but it's still dry. But now with that increase in temperature, it can hold more moisture again. So it hits the Earth, starts pulling moisture off of the surface of Earth, and it starts moving its way back toward the pole to complete this convection cycle. Let's jump up to the North Pole. What's going on up there? Well, cold air is sinking. It's creeping along the Earth, moving down toward the equator, picking up a little heat from Earth, and by the time it gets to about the 60th parallel, it's warmed up enough that it's starting to lift back up into the atmosphere. And as it does that, it again starts to move, it lifts, it cools, and it starts to spread out laterally. So a good chunk of this now spreads out, starts moving back toward the poles, nice and cold at the poles, it sinks again. So I've got another convection cycle going on up there, this time driven more by the sinking of the cold air at the pole. So what happens in between the 30th and 60th parallels? Well, here's where I get kind of that reverse gear effect kind of thing. Here's what I mean. Notice in this cell down here, it's rotating counterclockwise. And as it sinks at the 30th parallel, it kind of pulls a little air in from the other side of the 30th parallel, and it starts to sink and move down toward Earth also. Notice I've got a counterclockwise rotating cell here at the pole, but I'm at the other end of it, where the air is rising. So now, as this air rises at the 60th parallel, it pulls a little of this air from south of there, and it rises. So it's basically kicked off a cell in between these two counterclockwise rotating cells, is kicked off a cell in between that's rotating in the opposite direction, clockwise. So it's like gears, right? When you mesh gears together, as one turns one way, it forces the other to turn the other way. And you've got that same effect happening at both ends of the system. So I've got this in-between cell that kind of by default, because of what's happening at the cell by the equator and the cell by the pole, kicks off this other one in between, moving in the opposite direction. Now these guys have names, so you need to know the names, okay? So put a star in your notes. You want to remember these names. This cell right here by the equator is known as the tropical cell. It's also referred more as the Hadley cell, because Hadley was the scientist who figured it out. You know, we have NOAA here in the United States, the National Oceanographic and Atmospheric Administration. Over in Great Britain, it's the Hadley Center for Atmospheric Research. Hadley was a British scientist. He was extremely talented and was the one that figured out this rotation pattern later. The one up here at the pole is, as you might guess, the polar cell. That one's easy. And in between, this was the tricky one. This is the one that really kind of stumped everybody for a long time. But a guy by the name of Farrell figured it out. And it's also referred to as the mid-latitude cell because it sits between the 30th parallel and the 60th parallel. It's the mid part of the hemisphere. So you'll see those terms used interchangeably, and you need to know what they refer to. And whether you go from the equator to the North Pole or from the equator to the South Pole, those same three cells occur. And it's a band of this all the way around Earth, right? It's kind of like a ring going around Earth. Okay. Oops. Let's go back. But now we have this other little complicated part, this Coriolis effect we talked about, the spinning on Earth's axis. Does our weather come from the south or the north, or does it predominantly come from the east or the west? Where does it come from? Mostly from the west, huh? Sometimes from the south, sometimes from the north, but primarily it's west to east driven at our latitude. So the Hadley cell, the Farrell cell, and the polar cell explain north-south movement, but it doesn't explain east-west movement. That's where the Coriolis effect comes into play. And we already talked about that when we're talking about the oceans. So now we see from the 30th parallel to the 60th parallel, our mid-latitude area, we see Coriolis effect doing its thing in the northern hemisphere. Clockwise rotation, it's moving stuff off. So it's not just straight north or south, but it's clockwise moving over. Here we see that same other part. Here it's moving in this direction. Again, clockwise in the northern hemisphere. Southern hemisphere, just the opposite. So this Coriolis effect is overprinting the north-south movement of the air, giving it more of an east or west to east motion. So it's a little more complicated than it first appears. Now, I can kind of see a big global pattern due to these cells. Remember we said that cold, dry air was going to be sinking at the 30th parallel because it was coming down from the north end of the Farrell cell, the south end of the Farrell cell and the north end of the Hadley cell. That air was cold, dry, sinking to the earth. So if I look at the 30th parallels right through here, look at what I see. Big desert systems, the Sahara, the Arabian, all right along here. Same thing in the south. The Atacama, Patagonia, and the Namib, the Kalahari, the Great Sandy, and the Simpson. Big, huge, dry desert systems. Because this cold, dry air is coming down, hitting the earth, and sucking up the moisture. Kind of cool that I can actually see this effect of the atmosphere in the process. And Coriolis effect, as we had talked about earlier, clockwise rotation in the north, counterclockwise rotation in the south, and we see a very complex kind of pattern there when I put it all together. Let's just kind of go through a couple of these. This you need to kind of sit and look at a little bit. But essentially, here's our equator, here's our Hadley cell. And notice it's rotating counterclockwise here. And that means that it's creeping from the equator to the 30th. It's up in the atmosphere, isn't it? So as it's up in the atmosphere, moving northward, its Coriolis is swinging it clockwise to the right. So in the upper part of the atmosphere, that's the way it's going. But when it sinks at the 30th parallel and comes back to the equator, notice as it moves along the surface of the Earth, it's moving from northeast to southwest. Okay? Now, the same thing's happening in the southern hemisphere with the Hadley cell, but now it's going counterclockwise with Coriolis, And now what we see is as that surface flow comes back, it's moving from southeast to northwest. So the net effect is we've got air that's kind of coming from the north and the south like this, coming toward the equator. And as they meet, it basically gives us airflow at the equator moving from east to west. Look at the 60th parallel. Kind of the same thing in a way. I've got the polar cell, and with the polar cell, I'm looking at these guys up here. So as I've got the polar cell moving, it's doing the same thing as the Hadley cell. Remember, they both rotate the same direction. But the Ferrel cell in between, we said, was going in the opposite direction. So now what I see is the flow as it goes across the land is coming from the southwest going toward the northeast. And because of that, the net effect is the mid-latitude, the Ferrel cell winds blow not like the Hadley cells from east to west. Instead, they're blowing from west to east because of this opposite rotation. Okay? There's a lot of information here. You need to read through it and think about it a little bit. We just don't have time in class to go over it. But the net effect is I end up with these three cells, and I end up with different wind directions, bands of wind around the planet. The Hadley cell sets up basically west moving wind, from east to west. These are known as the trade winds. The Ferrel cells move air from west to east, and those bands are known as the westerlies, because that wind comes out of the west. We always name the wind after the direction that it originates from. So here, the west to east flowing winds coming out of the west, they're the westerlies. And then we're back to east to west flow at the polar cell, so there it's the polar easterlies. So we've got these bands of wind now blowing around planet Earth. Okay, true or false? Conduction is a much more efficient means of moving heat than convection. Here is we're moving the material and the energy is moving with the material. Convection, very efficient. Conduction, I'd just be taking, say, a hot metal bar and touching another cold metal bar, and the only part that I'd be seeing any energy transfer would be right at the point of contact. All the energy in the rest of the bar wouldn't be transferring, would it? It'd only do that gradually over time. So that's not very efficient. So convection is way more efficient than conduction. Okay, so here's kind of the model we end up with now. We have planet Earth. We have our Hadley cells right here by the equator, and we see the trade winds blowing east to west. Then we have the westerlies here in the Ferrel cells, and finally those big nasty polar easterlies at the two poles. Well, before we had days of steam-powered ships and oil-fired combustion engines, it was all sailing ships. And the sailors knew how to exploit these wind patterns. And this was kind of their life. If you wanted to go from east to west, you got in the trade winds. If you wanted to go from west to east, you got in the westerlies. You didn't get anywhere near the polar easterlies because they were just downright mean and nasty. And up in the northern hemisphere, all these continents got in the way. So they didn't come into play very much. It was the